My talk today is going to be about how we can learn about binary evolutions with special kind of transients that we call luminous red novae. My name is Nadejda Blagorodnova, but if you have trouble remembering that, if you remember my topic, red novae, and here you have some kind of broad nova, right? Like almost like red nova. So I think like the topic found me, so it's going to be much easier. Okay, so yeah, binaries. So this is the main question, right? We care about binaries not only if we are stranded, poor guy, which has like some binaries, they may interact and kill him. But from an astrophysical point of view, we also care them about like two main things, right? The first thing is that they are quite common, right? Even for different primary masses for our sun, already like about 60%, a bit more, is single, but the rest are in binaries, triples, or quadruple systems. And if we go to higher masses, these multiplicity fractions increases, and it's very rare to find a massive star living alone. So, massive stars like to be with a companion. And not only that, but it would be really boring if they had companions, and that's it. But what we know is that they do also interact. So if we look at here the frequency of different periods, this is log period in days, we see that, okay, low mass stars, they tend to peak at longer periods, but when we go to massive regimes, and this is the inner binary in multiple systems, the thin line, we see that for more massive systems, there seems to be a bimodal distribution for massive stars with a first peak at very short periods. So all these systems that are here on the left, they will actually interact. So this is again important because we care about massive stars, well, especially in the context of gravitational waves, and we see that they like to be with companions and they will interact. So what kind of interactions? Well, the interactions will lead us to a great wealth of like astrophysical phenomena that we love to study, right? Like we not only have like compact like white dwarfs, and we also can have like strip star, which are a source of highly ionized continuum for the early time universe. We also can have all kind of explosive events and high energy emissions, and that contributes in different ways. On the one side, it's a chemical enrichment of our universe. So having binaries actually has an influence, at a larger scale. We also have sources of high energy particles like cosmic rays, for example, and there is also the cold component of the universe, which is the ISM, which can also get enriched from products, these massive eruptions or planetary nebula from binary evolutions. So then the question boils down, like many of these systems are compact binaries. So then the challenge, like how do you shrink a binary, right? Like we have, for example, at low mass, we have cataclysmic variables, for example, systems with a carbon-oxygen white dwarf, together with a main sequence at a short orbit of half a day. So how this system formed? Because I mean, this core belongs to a star, which was a main sequence star, and this star would have expanded up to a red supergiant stage, it would be a much larger the actual initial orbit of that binary. So I mean, what the heck, they should be inside that envelope. Well, this is the main point. So then, if we go to more massive systems, also to go from this main zero image sequence to gravitational waves, we also undergo quite complex scenarios. But again, we have this same stage, right? Like these stars will end up orbiting inside of this shared layer of gas that we call the common envelope. And this will contribute to remove this orbital angular momentum to shrink the binary. So if we go a little bit back in time, like already like 76, Paczynski wrote a very nice article, right, about this common envelope binaries that he basically said that, right, like when the stellar surface moves outside of this outer Lagrange point, well, there will be a common envelope. The two nuclei will kind of spiral inside this envelope towards each other, draining the angular momentum, and the final separation can be much, much shorter than the initial one. So for this to happen, right, first we need a binary, this one will expand, which will feel its own rush law, right, which will reach this Lagrange at one point, it will start transferring mass, then we'll have a contact binary. Like in both these cases, the envelopes are co-rotating with the binary, but then at one point when the mass fills this L2 rush law, Lagrange point, then we will have like a loss of mass from that system, and that's at a very, very efficient sink of angular momentum. So basically, the envelope will stop co-rotating, and then these two stars will kind of spiral and transfer inside. But then to reach this scenario, what do we need? Well, we need unstable mass transfer. And these are two concepts that we need to understand. So in order for a binary to start transferring mass, there are two possibilities. Well, the first one is the donor star will need to expand, and stars do expand. So this is an evolution of a 5 solar mass stars. This is an HR diagram. This is the main sequence. And then it moves up to the red giant branch. When it finishes hydrogen core burning, it ignites the shell burning, and it will expand very, very quickly. So then after this, it will spend sometimes core helium burning, and then will expand again. So then depends on what stage of expansion you are, you can initiate mass transfer towards the companion. We call it case A, B, or C. So this is not the only thing. Like then also you can expand the donor, or you can shrink the binary. And you can shrink the binary. There are several mechanisms for draining the angular momentum from the orbit. One is emission of gravitational waves, but we know that works when they're quite close. We can have magnetic fields. We also can have a spin-orbit exchange. So when we have a tidally locked binary and the donor expands, then basically we try to kind of spin up itself, and it will extract the orbital angular momentum from the donor, which can actually lead to runaway and Darwin instability, which can actually lead to the merger. And finally, the mass loss. If we lose mass from that binary, we also will shrink the orbit. So these are two main cases. And the second thing that should happen for us to have a common envelope is that the mass needs to be unstable. So here we have mass transfer stability. And for that, we need to have kind of into account three different things. The first one is the response of the donor's radius to mass loss. And this highly depends on what is the envelope structure of the donor, because basically for example, convective envelopes, they have an inverse mass ratio to mass. So then when you remove mass, they expand. Radiative envelopes will shrink. But also we need to balance that with the orbit response. So when you transfer mass between companions, your orbit also shrinks or expands. And finally, the accretor responds as well to this transfer mass. So I will not kind of cover this, but this can be pretty interesting to explore. So then all these interesting things bring us to several challenges or interesting points in binary evolution that we still yet not understand. So we want to know what binaries will actually initiate this mass transfer from all bunch of possible configurations for that period distribution, which ones will actually initiate mass transfer and how conservative this mass transfer will be. Right? So this sets up the rate of how many single stars we'll have, how many strip stars we will have, and how many merger or compact systems we will have. Like the next challenge or big question is like also what is the structure of these stars, how they look like when they enter common envelope, because that can alter dramatically the output. Having a big envelope is not the same as having a small envelope. And then how this envelope is ejected. So in this case, what energies are at play to help us to eject this envelope at a radius when the gas is unbound. So this will also set up how many mergers versus how many full ejections we will have from an initial population. And finally, what is the remnant? So when we have undergone all this, the remnant will also have some properties. It will provide likely some extra gas into the ISM. It may form dust. It will release some extra elements form. So how this can enrich the universe. So all this is important because we still don't know many of these, right? We still have huge uncertainties on rates of binary neutral stars. We still don't know which ones are entering common envelope, which survive, which don't survive. Also, these the highly ionizing flux from the strip stars. Also, is like how important is it, how it competes with AGN or galaxies. This is important. Like about the second point, yeah, like the envelope structure is also important because and the energies, because until very recently, all hydro simulations failed to eject an envelope. They would just release a little portion and the rest would fall back. And recent work show that we need to consider extra energies, recombination energy, radiation pressure energy, and so on, so that really can help to eject the envelope, plus some dust-driven winds. Yes?
So I think I missed something. It's a problem that they're not ejecting the envelope? Like we know they should and they don't?
Yes. Yeah. I mean, these are like, they would simulate red supergiants with a companion that in principle should eject the envelope, but they would not succeed.
Okay.
So when new work started to put recombination energy into these simulations, they actually succeeded ejecting the envelopes, and that was, well, I mean, this is highly debated in the field, like what more energies you should consider as source and what energies are the sink. So there should be a balance, so you should achieve some successful ejections because that's what we see in nature. And also, yeah, we still don't understand common envelope, right? Because if we consider the population of pre-common envelope binaries and post-common envelope binaries, we cannot reproduce the periods and eccentricities of systems that we know they are post-common envelope. So there is still some physics missing here. And finally, the remnants. So if we consider that like there is some chemistry involved in all these binary interactions, each channel of binaries should provide some chemical enrichment to our Milky Way, for example. And there was some work comparing different binary population synthesis code, and they all failed to reproduce the chemistry of the Milky Way. So there's still some physics that we don't know. And then also the ISM has too much dust. So the ISM has dust that cannot be accounted from AGV or core collapse. So maybe binaries can be the question, but maybe I'm just overly optimistic. But common envelope is great. It's very important. It's very hard, and we want to study it. And that's why many very clever people develop like great work. But always it has been like a piece of a puzzle, right? We want to understand this, you know, like before L2 mass loss, how the donor evolves, how the accretor evolves, you know, what is the mass exchange, when it becomes unstable, for what binaries becomes unstable, right? Normally you do that with MESA. Then you can do simulations to see from beginning of kind of rush lobe overflow to L2 mass loss, what happens, how the system loses, you know, angular momentum already before the common envelope stage. Finally, you have some well, common envelope kind of self-regulated phase that we still know pretty well. And the most loved phase, of course, is the dynamical ejection of the envelope that many people simulated with more or less energy help to eject. So this is a great puzzle, but the problem is like each piece has been treated with different codes, with different binary system, with different assumptions. So in this case, we need a ring to rule them all. And this ring is these observations, right? So I mean, I'm an observer, I need to advocate, but when we have a system, if we can observe all these phases, then we can actually put all these codes together under the same initial conditions so that they all need to match, right? What we actually observe. And this is the importance of observations because they actually provide us a baseline and provide a final text. I guess you're familiar with this image. So this was one famous luminous red nova called V8381. It was like kind of a more or less massive merger, and the luminous red nova is this thing in the middle. And what we see around here is a light echo on the surrounding material because it was in a kind of young stellar cluster. So where do luminous red nova live? So if we have this known parameter space, this is the time scales, and this is the absolute luminosity. And assuming something like ZTF, I don't know if you're familiar with the time domain survey to detect transients, with its sensitivity, we can see them up to, I don't know, 100 megaparsecs, and they live in this kind of banana thing. You will see them later why. So we call them gap transients because they're between core collapse and classical novae, kind of in this gap, along with like other transients. And here in the bottom, we have a low luminosity guy that it's been very, very important for our research. So this object called B1309 SCO actually was kind of the Rosetta Stone for us to link these observational transients to actual binary mergers. And why do I say that? Well, it was monitored by the Ogle survey. It was in the fields of this microlensing search. And they saw that there was some kind of scatter, and there was like some brightening, and there was this nova, which was red, low velocities, and so on. But the authors of this paper decided to break the light curves per year and fold the period to find the periodicity. So they found that it was an eclipsing binary that had this signature, but also an amazing thing was that the period kind of had an exponential decay just before the actual burst. So this was the ultimate proof that the system was a binary that was quickly kind of shrinking, and then it had the burst. So these light curves of the progenitor allow us to actually infer what would be the characteristics of the binary. So some of the properties that they were derived is like the primary was about 1.5 solar mass, and the companion was about kind of 10 times less, like Q equals 0.1. And all these people advocated that the actual merger happened because the primary star, the more massive one, was kind of evolving out of its main sequence. So then this star would expand, and then, as I mentioned before, there is this exchange of spin of orbital to kind of spin angular momentum that would lead to this runaway process, which we call Darwin instability. Then the orbit shrinks, then we start to reach this Lagrange point, as Paczynski said, and then we start losing mass, and when you start losing mass from L2, you're doomed. So the merger is imminent because a super efficient shrink of angular momentum. So this is one scenario, and the other one is actually a bit more convoluted. It says that the actual star that evolved was M2. So here the authors advocate that there was a star 1, it was evolving, and then it started to grow, but then on thermal timescale it transferred mass, and then it kind of, they detached, and then, well, they started to evolve separately, so nothing happened until the second star started to evolve. And then again, the growth of the secondary star, which had an already inverted mass ratio, was the one that started to initiate this spin exchange again, Darwin instability, and L2 mass loss. So, I mean, there's like two different scenarios. I mean, we still don't know which one is which. So this was unfortunately one object where we really saw this period. We really hope to find more. But what can we do right now, right? In the galaxy, we have only 4 or 5 maybe galactic of luminous red nova. So we really need to go outside of our own galaxy to find more of this. So if we want to understand what happens to these unstable binaries, we can look for luminous red nova, and then we can look what was there. I mean, as you can see, this is one of the spiral arms. This is M101. And these objects tend to be quite far away from the cores of the galaxy, which makes me think there's probably some metallicity factor. But yeah, when you find a luminous red nova, you can go back to your archive and see what was there before. Oh, look, there was a star. And then 2 years later, it was gone. So then you can say, okay, well, that was my progenitor. So the next thing you can do as a good observer is to model your SCD. You can take your favorite black body or stellar model. So then you can derive like some kind of temperature or luminosity for your object. And I was, to be honest, like a bit surprised initially because I was like, what the heck, this is the main sequence, the red gem branch, and these objects sit in the middle. It's very unlikely to find a star in that position of the HR diagram because this is 3,000 years of lifetime of the stars. So it's kind of running through the Hertzsprung gap, and it's called gap because there are barely any stars here. But then if you remember the growth in radius during case B mass transfer, when the star is here, its radius kind of grows like an order of magnitude. So then it's not very unlikely that if you have a companion and the stars expand so quickly that you will inevitably run into unstable mass transfer. So then, this is was one progenitor. Now we started to compile more data about other objects.
Sorry, I missed that story a little bit. That you're saying that it's more likely to undergo this process during this few thousand years. That the point of that? Okay.
Yes, because when you are at the main sequence, the star grows on like kind of nuclear timescales. So that is a very slow growth. So in that case, if you have a companion, you can send some mass and the companion can accrete it, like no problem. It's a very slow, little amount of mass. But if you are in this kind of asymptotic nearly growth of the radius, there is no way the companion can accrete that mass, neither with jets, neither there's no way. So it's a lot of mass that is going to be dumped on the companion. So you inevitably will fill all that surface and reach L2 point and start losing mass, and then you're done. Okay, so it was interesting actually to see that like all new systems, again, they're falling here. And like maybe this is the reason, right? Like in main sequence, there is more nuclear timescales, mass transfer. Here is on thermal timescale, which is much shorter. And here, why don't we have anything here? And that was a puzzling question initially, but then you can also think, okay, we are identifying this with optical transients on rather short time scales. If you're a red supergiant, you're very large and like nearly dust enshrouded star. So if a star is very far away and it's a companion star that entering your envelope, all this process will be very slow. So it will take years. And by the time you can reach more region where you can actually exert some work on the envelope, you're likely is going to be enshrouded by quite a lot of dust. So then this, the full common envelope ejection, what we believe, or like with the yellow red supergiants, are likely enshrouded by dust, and therefore they are more likely to be identified by infrared time domain surveys, not by optical ones. Okay, so the next question that we can ask is, when we have a progenitor, as I mentioned before, you get the SCD, you put the HL diagram, but again, this is wrong. You know your transient was a merger, so then why you're doing that? Well, because we're observers, okay? It's very easy to download the MIST model and make a single evolution tracks and so on, but we can do better, So if we put a little bit of effort, then we can start using something like MESA, you can have like binary evolution models. And then you have a parameter space from your observations, and you know your binary progenitor. Let's say this guy was 10 years before the merger, was sitting here. So then the question you can ask is like, what binary configurations can lead you there, right? So for different primary progenitor masses, for the donor masses, you can see what mass ratios of the companion and what periods, right? Because this is related to what period kind of what distance the companion is sitting that you can start transferring mass will lead you here. And from here, we can see that, well, the parameter space is restricted, but it's not zero. And what we see is that when you initiate mass transfer, the luminosity of these stars drop dramatically. So you're transferring mass. This mass transfer rate is pretty large. And what happens to the star, just it's losing mass, so it needs to readjust to this mass loss. So it needs to regain equilibrium. So then the energy of the star is spent into this re-expansion and readjusting rather than.
Sorry to interrupt you again.
Yes.
I'm trying to read this. I think what's going on is the donor star evolves to the right. It has a color, but that color bar only kicks in once it starts actually accreting. Is that? Well, I'm just trying to understand what the line
is. Mass transfer rate. So these are donor stars. So then they encounter a companion at this period, this distance, and they start to transfer mass. And this is the mass transfer rate. And then the color
of the line is reflecting the mass transfer rate past that point. Okay.
Well, when you, I mean, if you haven't met your companion, you haven't expanded beyond your like L1, there is no mass transfer rate. So when you reach the L1 mass point, or you have exceeded your Roche lobe radius, then you will start transferring.
I was just trying to understand the colors of the lines.
Yeah. Well, I hope it's, I mean, up to this point, there is no mass transfer. So we wanted to differentiate them by colors, but here is like mass transfer rate.
Okay.
Just to show that this is huge. Yeah, the purple color is a lot, right? So at the time of the merger, then there is a lot of mass transfer. And the important point is like this guy may lose several solar masses when it gets here. And that goes back to my first point. What is the structure of the envelope when the merger happens, or when the common envelope happens, right? Because it's not the same here. So, that star lost 3, maybe 4 solar masses before reaching this point. So the structure of the envelope is definitely different from when it started to transfer mass. So from MESA, we get that. And the other important thing is like, we know the structure of the envelope, we know the velocity from observations that the ejecta has. So then we can estimate the energy, the kinetic energy of the ejecta. Plus, we know from MESA the binding energy of a fraction of the envelope mass going from the surface inward. And because we know the donor kind of mass and we know the mass of the companion, for a given donor mass, we can take different mass ratios for a companion and just see, okay, this binary had this orbital energy. if I put that orbital energy into ejecting this fraction of the envelope with this kinetic energy, how much mass can I eject? So basically, just from the mesa alone, then you can estimate a range of ejecta masses that this object can have under different assumptions for the companion. We don't know what the companion is, but we can estimate the mass range. Like, this is definitely not the envelope of the donor. This is just a fraction of a solar mass. So then that means that all these are just mergers. This is not the envelope. The envelope is pretty much still with the donor, so we just ejected a little bit. So if we go back to our friend B1309 scope, we commented on the periodicity, but there is a different thing here. There was like this brightening. And this brightening is again very interesting because we mentioned that L2 mass loss happened just before the merger. So if we imagine that this brightening is actually related to kind of this mass loss, the mass loss accelerates with time. So then it kind of self-shocks and self-intersects. So then it can also create an additional source of radiation for these transients. So we will see this slow increase in luminosity. And this is what we call the precursor. This is the precursor emission. So if you have the orbital evolution and you have the appearance of this guy, then you can, for example, simulate, different different SPH, what kind of mass loss would agree to provide the binary light curve that you see. So here the different estimates, and as you can see, the tail of this mass actually starts to occult the small star. So then you start losing this secondary peak for the star, and that's what they saw in the observations. So this is pretty cool, but again, this is our kind of unique object with high temporal resolution. We can go again outside of our galaxy and look for more luminous red nova. And we see that's interesting because if we have the sensitivity, and these are M31, M101, so they're very close by, if we have the sensitivity in our survey, they all show this kind of small increase in the brightness before the output. So that kind of, it's quite conspicuous. It tells us like, well, if the merger is caused by L2 mass loss, and L2 mass loss is causing this increase in the radiation in the system, then we should see this precursor in all luminous red nova. And this is pretty cool because like people have talked about predicting supernova, but that's very hard. But as you can see, it may be not as hard to predict luminous red nova. So we are kind of on the hunt on. So again, I said like extragalactic things are faint. So if we look in our own galaxy, can we see systems in this precursor phase? I mean, the rates are one of these luminous red nova every 3 to 10 years. And if the precursor phase lasts about 5 years, it's not impossible to find one system in our galaxy that is in precursor phase. So starting from this hypothesis, we can use some Gaia data to select some sources that would be in the Hertzsprung gap, and they're likely then experiencing that stable mass loss. We checked variability from different time domain sources for sources that would be brightening. And then we analyzed their estimates. Yeah, to our surprise, many had this infrared excess here, showing that likely there was some kind of dusty disk around the system, which made us very happy because that's what we expect. If you have binaries, transient mass, it's going to be messy. More of them like had emission lines, which made us even more happier. Okay, you have excitation of these hydrogens recombining, perfect. So then we happily wrote a proposal for high resolution spectra to test, what these systems were, expecting to find something pretty nice. Well, we found strong hydrogen emission lines with some absorption, which is likely kind of some disk, which is edge-on that is obscuring this. And we found helium-1 lines, which tells us that these stars are hot. They are not yellow, definitely. Helium-1 appears on B-type stars. And we followed up the light curves. We detected them here in the previous paper. So now we took the spectra here. We see, yeah, there was an increase, but it went down. Well, what these things are? Well, unfortunately, they are big stars, all of them. I mean, we're making somebody happy, not us. But you know, they were here when we selected them. When we correct for extinction, they all go into the main sequence location. So this is upsetting, but this is tells us that, you know, looking for these yellow stars in the Milky Way, it's very hard because extinction is a bit problem.
Do you think they're self-obscured, or do you think they're just ISM obscured?
I think it's ISM, and yeah.
So boring obscured.
Yeah, exactly. I mean, I was excited thinking that it would be ISM obscured, but yeah, I mean, here I didn't want to go into details, but this is the extinction that we calculated from diffuse interstellar bands from spectra. And this is a new catalog based on Gaia data, which has a better treatment of extinction based on more careful kind of modeling. And if there would be like self-obscured, I would expect that the extinction would go wrong because they kind of consider that the stars are in the same region of extinction, like for a patch of a galaxy. So yeah, I think that's for sure. So, well, you know, we didn't get this course, so we tried to look for more stars, and in this case, not only brightening ones, but anything which was likely variable based on large error bars in the Gaia data. So we analyzed also the new release, which has some emission lines with very low resolution, and we also look for excess in the mid-infrared, again, hoping to find disks. So again, we took some light curves and spectra, and again, you know, this was our initial selection, the red data points. When we correct them for extinction of this new kind of, you know, reprocessing of Gaia data and so on, many of them go here, but we still, like the black stars, indicate the corrected position. We see some become red supergiant, but still we have a few in the yellow regime, which kind of gives us some hope. So the next things that we did is like for the periodic ones that were likely kind of eclipsing binaries, we have here the observed period, and star horse provides us an estimate of the mass and the radius of the star. So if you have these two things, you can estimate at what period that star would be filling the rush law. So this is this quantity. So this line indicates that not filling the rush law, and these ones are filling the rush law. But because we don't have radial velocities, this could be also pulsators. So yeah, we would need radial velocities on these guys to know if they're actually moving or there is sinusoidal variation because they are just pulsating.
Can I ask something about the statistics really quickly? So
yeah.
So I mean, you expect in a given population a certain number of Hertzsprung stars. And is your statement that the ones that we're showing these outbursts are obscured, not that most of the stars in there are just obscured BE stars, that just the ones that you were finding that were showing the time variability?
Well, we didn't look for nearby stars if they were similarly obscured.
Okay, I guess I would, okay, we can chat about it afterwards.
Okay. So the next quest for this precursor is actually to indeed turn our side to outer galaxies. So, well, hello, I think it's very interesting. Yes, so for this purpose, we decided to identify yellow supergiants in nearby galaxies. So we used HST archival data to compile like 200,000 candidate yellow supergiants in nearby galaxies, which is more or less kind of complete for masses superior to 8 solar masses. So then we use this catalog to cross-correlate with like ZTF time domain data. And we have a few of these yellow supergiants that again show some interesting rising behavior, which is pretty cool. So we have a spectroscopic proposal accepted for getting spectra of this. So we'll be able to confirm whether they have something to do with our yellow supergiants or not. And also it will create a nice watch list for the future. So if we have any transients associated with these yellow supergiants, we will give them more careful look than if they are just in the middle of nowhere. Okay, so going from precursors, now the next stage is the outburst. So this is more or less how they look like. They have a quick blue peak, which is hotter temperature, and a kind of slower red peak. So if we look at the spectroscopy, I mean, this is a kind of black body. This is shorter wavelengths, longer wavelengths. So the peak of the emission is kind of in the UV, and there's strong Balmer lines, which are centered kind of on the rest kind of wavelength. As we move through the red peak, the temperature drops down. So then the temperature is more like our sun, 6,000 Kelvin. And at very late stages, they look like M, kind of very cold stars. So all these throughs is like a molecular absorption from molecules forming the star. And here we see very late times is like the emission peak is in the infrared. And also these are emission lines, and we see them, they are blue shifted at later stages. And this tells that there is dust formation in this system, right? If we have some gas expanding and dust is formed in the system, then the part which is receding from you will get obscured by dust. We only will see emission that is coming towards you. So then what is powering the light curves? And this is something that Brian did. So one of the possible energy sources for light curves is recombination. We consider that we have shells that are expanding and recombining, and after the first release of thermal energy, we have subsequent sums of different shells that are recombining, and when you sum them up, you make a plateau. Well, this is all nice, but then when we go to the most massive events, where here we have the donor mass, and this is the ejecta mass needed kind of to power the light curve, we see this is 1-to-1, and the more massive events, they would need a larger ejecta mass to power the light curve than there is in the actual star. So this is not possible, and that is a telltale that we need an additional method to keep the luminosity of these transients. So shocks is the most obvious one. Again, Brian's work, thank you, Brian. And in this case, I mentioned we have L2 mass loss, so then we have this fast release of this ejecta during the merger. It will crash into this slow wind, and it will generate a shock emission. So again, we have like the cooling envelope phase, and then we have the shock, which can also help to provide additional energy to our transients. So what do the observations say? Let's go back to our, again, friend, UV13 and Mexico. And here we have an analysis of very exquisite resolution spectroscopy. So as you can see, there's like no evolution, and this is like kind of a slow velocity component. What they say is like, well, there is a fast velocity, which is the actual ejecta, is 200 kilometers per second. But then at 50 kilometers, more or less, we have a curtain of gas, which is sitting in front of your light bulb. So the merger happened behind this curtain, and this curtain only kind of interacts with the merger through receiving this radiation. It gets ionized, but then basically this gas is not changing, and even at 400 days, we don't see any interaction between the fast and the slow component. And this tells you two things. Either they are orthogonal, so they don't interact, they move in different directions, like maybe like a ring and a bipolar ejecta, or they're really far away. So at 400 days, they didn't reach each other yet. So extragalactic is also the same. We have some series here, and you see like this narrow kind of absorption. They still persist after like 300 days. And we looked and we looked and we looked in our spectra, and we do not see any lines that are normally associated to shock interaction. Meaning, we just say we need shocks to power the light curve. This is massive events, but we don't see the shocks. What's going on? So again, maybe either like not interacting, but we would need some interaction to power the light curve, or maybe the density is too high, right? Because many times when we look for lines that are shock telltales, they are in low density environments. And these are forbidden transitions that are not collisionally de-excited. So then if we have high density gas, it likely will kill all our telltale lines. So we will not see them, or the shocks are behind some gas that it's obscuring the shocks. So the shocks are propagating, but we don't see them because it's in an optically thick regime. So we need to figure that out.
Yeah. On the low velocity stuff would be the far away stuff in that second model. And it's being, would you be able to see like a reverberation mapping effect on H alpha if it's being ionized at like some particular moment? Like, would you see?
Yeah, I mean,
I'm not sure exactly how that would work.
It's because they saw that this curtain already was ionized at an early time, right? So the light travel time already ionized this curtain when they looked at the spectrum. So this is the distance they derive. So they say it needs to be closer than this distance, because when we looked, it already received the radiation.
So they didn't, right, okay.
Yeah, so it already ionized part of this curtain at a given time. I don't remember how many days, but this sets up the kind of the upper distance at which this gas should be.
Okay, but they don't have multiple spectra, so they don't know the actual length of that.
Yeah, well, I mean, they have a bunch of spectra, but the earliest spectra is the one that sets
Is the one
this
that's-
time.
yeah,
Yes, I
okay,
mean, they assume like there's no diffusion, right? Without diffusion, light travel time, this sets at the maximum distance
I
at
see.
which this gas it is. So the
Okay.
first spectrum you took, you already saw that it was ionized by the radiation, so that
Okay,
means that.
so it could be much smaller than that.
Yeah.
Okay, thanks.
Okay, so then if you look at the light curves and you start to do some population things, you know, what we see is that this is brightness of the event. It's correlated with what we can estimate for the progenitor mass from these archival data. So brighter events are more massive stars. Also, brighter events have longer plateau durations, and brighter events also expand faster. It is kind of makes sense, you know. More massive stars will have larger envelopes, so you need more energy to eject them, and they will last longer. But it's nice to see that it's here. Okay, going back to this guy, which I said we did not see any shocks. We were not patient enough. You know, after 9 to 12 years, you know, Kaminski and his student, they decided to take ALMA observations, which trace molecular gas, which is very cold, like a few tens of Kelvin. And they did see that there was, first of all, two lobes, like, you know, it was kind of a bimodal ejection. One was red shifted, the other one blue shifted. But the most interesting thing is that they actually did see interaction. So they did see that this there was formation of H2 and then also some dissociation. So each lobe kind of worked differently. But basically, this was pre-merger material that was sitting like pretty far away from the actual event. So this is a bit of a puzzle, you know, what created this material, why it's sitting there, and it seems that like 9 to 12 years, the ejecta is finally interacting with some of this material. So if we look for another object, this time it's a much longer one. So this is our best candidate so far for a red supergiant luminous red nova. It took 4 years for it to kind of do its own thing. But we did see the optical, and that's actually the interesting thing. But again, if you are like patient enough, like 18 years here, and you look at it in different, well, this is like a whole complete SCD from like mid infrared to far infrared using different compilation of instruments. We see that, well, first of all, the best fitting model is again two shells. A colder shell, which is sitting like, I think it was 9,500 AU from the merger, like quite far, and it's cold. And then we see that there is this merger ejecta, which is expanding with the velocity of the merger that we infer from spectroscopy, and it's a bit warmer. And then there is a cavity. So they tried for disk models, okay, there may be a disk, but they don't fit, as you can see. So, well, they estimated the mass, and it's 0.12 solar masses of dust for a progenitor, which could have been, you know, 1 or 2 solar masses. So this is big amount. And it's like olivine silicates and iron dust. I mean, I saw there was like a visitor talking about iron dust. I want to know more. Okay, so it's again like the same kind of structure. We have some pre-existing material, which is really far, and then we have the merger, which still didn't reach. So I mentioned 0.012 dust mass and why this is important. So I talked before about the ISM, right? The cold component in our universe. And we do care about this because here are the measurements like of the dust content in the Milky Way in the ISM. And these are different contributions. So like from AGV star, which are low mass stars, it takes a lot of time for them to evolve, but there are many of them. Or core collapse supernova, which have large ejecta masses. But then there is reverse shock, which kills like 80% more of that dust, right? So if you see that there's no reverse shock, which is not physical, you reach the amount of here. But if you consider reverse shock destruction, then you don't get here. So there is some dust in the ISM that is there. Like people have been saying, okay, the ISM forms dust by itself, but then the binaries maybe could be the solution. So if we have our light curve, I mean, this is maybe some critical, but this is optical. So as you can see, it goes away, like, I don't know, there was a month. Then this is near infrared, and these are like Spitzer observations in mid infrared. So they last years. So then what we can do is to try to fit kind of spectral energy distribution, some dust radiation transferring model to estimate how much dust do we have at each time. So we also did that with JWST data. So for different primary masses, like 15, 24, we wanted to kind of cover a bit of a range. We estimated how much dust they did produce after some time after the main eruption. And here you can see how much dust each event produced. And this is the average of core collapse supernova. So we can see that, well, you know, it looks like they're like ramping up. So they're approaching the core collapse supernova. And this is early time, right? Because these things keep cooling and keep making dust and keep cooling and keep making dust. And this Ogle guy, which was a 1.5 solar mass star, look, it produced nearly the same dust as a core collapse supernova, which was a very massive star. So if we account for the amount of luminous red nova, which the rate is comparable to core collapse supernova, so like 1 per century per Milky Way galaxy, then we can say that at least at these early stages, when we have still little dust, they contribute at least 25% or more than core collapse supernova. So we should not neglect them as sources of dust for the ISM. And well, this is a paper by Viraj. It's going to appear in the archive soon. So if you're interested in a few days. Okay, so yeah, I will take a few last minutes to just cover the observational landscape. I think you're familiar with ZTF, so this has allowed many great discoveries in the Northern Hemisphere. There's also Winter, which takes near-infrared photometry for transients, but maybe you didn't know about the Black Gem, so this survey has started like a year ago. And there is an agreement that we actually will look 3 times a night at a grand portion of galaxy that have HST data and they are closer than 50 megaparsecs. I mean, this will guarantee that if a luminous red nova happens there, we will have exquisite time coverage in multi-band photometry so that we can not only study its progenitor from archival HST data, but we will also be able to derive whether it's a periodic, again, eclipsing binary, and we will be able to see if it has any changes in its period. We are monitoring, we are waiting. Non-luminous red nova has blown up yet, but you know, we are hopeful. And of course, we should not neglect the imminent future, which is Rubin, LSST. We have here the coverage. This is the dusty galactic plane. We're not going to look at there, but there's going to be many observations here. The cadence is not as good, of course, as the other surveys, but it's going to be a 10 years baseline. And the important bit, we are now here in May, and in April, look, Rubin on sky engineering. Like every time I look at this diagram, it always delays, but voila. You know, on the 17th of April, look at the faces. They look surprised. I think it's good. You know, after so many delays, they're like, wow, this is real. You know, so yeah, I'm very excited. You know, like if everything goes well, by the end of the year, we actually will have like all these transient alerts and things streaming to us, which is great. So this is like kind of like a lookup, right? Like now we see the tip of the iceberg. You know, all these surveys, they go shallow. So we just see the actual transient. If we're lucky, we can get some infrared data. But then LSST will help us to go this. This will be for free, more or less. I'm not in the collaboration, but you know, alert is going to be available. But you know, this is going to be covered. And the cadence of LSST is garbage. Sorry, I didn't say that. But you know, for long precursors, it's going to be great because we don't care. You know, it takes us several years for us to increase in luminosity. Cadence 1 week for supernova, disaster. For luminous red nova precursor, beautiful. And then we also have the progenitor information from LSST. So in this case, we don't even need HST. You know, we can take it from LSST. And of course, our era is in JWST, so we can not only like study progenitors, precursor, burst, and we can also study the dust. So I mean, the future is very bright, but there is a problem. I said that was like a bit like an iceberg, but I think the actual situation after LSST stars is going to be something like that. It's going to be some big discovery, big chunks of ice, but the majority of things are going to be these little pieces of ice floating. So question, which one do you want to jump on? Which one is going to save your life? Which is going to be your great nature paper? You don't know. There are so many of them. So you need kind of a strategy. Well, I hope that we have one. So the first one is the one I mentioned. We have a yellow supergiant catalogs. So from these 10 million, the ones that are linked to a yellow supergiant, we will care about. Also, we are compiling a kind of compilation of galaxy catalogs, and we are cleaning it up to make the best kind of galaxy catalog with distances and kind of mass estimates for up to 2 gigaparsecs. So all LSST alerts will be cross-matched to these catalogs to find our gap transients in that luminosity regime. And we're also exploring the use of machine learning, because there are going to be even so many things that we will need, 100 PhD students or a machine learning approach to actually look for all these light curves and identify our progenitors. So yes, this is my final slide, and there's a fishing slide later on, but yeah, so I hope I convince you common envelope is a very important phase in binary evolution that has many implications on many other important research questions that we have. And if we want to understand it, we should also look at the observations that can provide this framework to put all the pieces together. So luminous red novae are these common envelope transients. So their progenitors will kind of, with the time, reveal the parameter space where all the unstable systems are, because they are going to be mergers. The precursors will allow us to test, how this orbital period changes with luminosity and make all these beautiful simulations. And then the properties of the outburst also will finally reveal us what are the energies involved in projecting this envelope, what are the geometries, what are other kind of mass around these systems. And also the remnants will show what is the final geometry of the remnant, how we can contribute with the dust. So yeah, common envelope transients, progenitor, precursors, and properties of the outburst, C3PO. So this is my year project, and thank you for your attention.
Thank you, Nadia. We have time for some questions.
Thanks for the excellent talk. I was curious about your plot showing the growing dust mass. And I'm trying to understand, is this observationally what dust, I can imagine different reasons the dust mass would grow, physically, but is it just a matter of the ejecta is optically thick and you can only put a lower limit on the dust? Is this, I guess what I'm going to ask is this, you think the actual total dust mass is doing versus time, or this is like what you can
because
measure?
we see the dust is cooling. So the ejecta is cooling, and as the ejecta is cooling, you have inner gas that initially was hotter, also cooling beyond the dust condensation.
Okay, so this is something, that's what I was saying. So you have a multi-velocity ejecta, and the fastest stuff reaches the dust condensation temperature earliest, makes a little dust, and then as time goes on, more and more material. Okay, so it's not just measured. It's not like measured lower limit on the dust. It's the actual dust mass.
Yeah, because this is dust radiation transfer code. So you actually have like a source that you put inside that has like some luminosity, and then you assume a dust kind of density profile. But that all the radiation from the source needs to go through the dust. So then basically you can kind of measure what is the dust mass from that.
Yeah, so this morning, the Galaxy's visitor, Caleb Chobin, yes. He was also worried about the growth of dust over time. And he was very satisfied in the Milky Way because he was not looking at those plots, but he was worried about high redshift. And I don't know, I just thought you might talk to him because he was not in his models. He does like these simulations and they put in dust growth, but I don't think he had binary production like this in his. So if he's still in the building, find him.
Thanks.
I think the key process in his model was gas phase accretion. That's where he got most of his dust mass.
Yeah.
More questions?
Maybe I can just adding to that. I mean, supernova are a very prompt source of dust. So if they make dust in high redshift, they can do it quickly. These guys have a whole range of sort of delay times, right? You have some solar mass stars, some 10 solar mass stars, you know. And so I know I asked you this earlier, but do you have a sense of where, you know, I know the more massive mergers are rarer, but they also eject more mass.
Exactly.
So there would be some contribution of prompt dust formation and then some delayed dust formation. So
Yeah.
do you think that the massive stars that would be able to compete with core collapse in terms of their timing are competitive?
I think so. I mean, because they also mention like LBB eruptions, right? They are so rare. They're like very massive. They're very rare. But when they eject something, that something is very big. So then LBBs are also like not in this AGV thing, but I mean, they also high contributors. So like similar to LBB, stellar mergers, like at least the massive ones, are more common than 50 solar mass stars. But already like a 10 solar mass can eject like one mass that can form like a significant fraction of dust. Yeah, I think like we need to do a bit more in detail, like all these calculations, you know, with the IMF, and also I feel we need to look over the initial progenitor mass or the envelope mass, you know, to see like, let's say scale, like, yeah, normalized by the initial mass of that star.
So I'll ask a question. Are there any either Milky Way or extragalactic luminous red novae that we think are successful ejections? Or are there any systems where like there's evidence of a surviving binary?
Well, I
long
mean,
after?
Luminous Red Nova, no, but we have planetary nebula with closed binaries in the core. So, I mean, those are successful ejections, but they are like few thousand years old. I think there was this ring nebula that maybe was a bit younger that like Brian and collaborators explored. That was, the only problem is this, right? Like if they're successful, they have very expanded envelopes, so they are likely red supergiants. I mean, now Viraj has actually a paper about one possible thing that could be like a full ejection, because it's like it's very slowly brightening still, and it has kind of yeah, very slow expansion, and it doesn't look like any other kind of slow varying variables in the Milky Way. So it has a very peculiar behavior. But we'll need to kind of, it's not a smoking gun, it's a candidate. But yeah, we haven't seen anything that we can say yes, like not like B13 on Expo at least.
Great. Any more questions?
But if not, I can show my fishing slide. Ta-da! This is what happened. Like when you have like all the proposals in place, like you want to fish for something and then you get another fish. So we're like looking for luminous red nova. That's why we selected this burst, right? So we took a bunch of spectra, spectropolarimetry, everything. We're very happy. There's like, you know, low velocities, beautiful. And then it disappeared. Like I was pissed. And then it reappeared as a like type 2N supernova, you know, and you can see like, again, like this is beautiful data, like high resolution. These like two absorption components. They are in precursor here, and in the before, kind of around here before peak, we still see them, but after peak they're gone. So we have all the ejecta like kind of overtaking this mass loss. Yeah. So I mean, I will have to write this up. It's not a luminous red nova, but you know, it's super interesting. So yeah, you can get some other gems when you're fishing for something else.